Hi everyone, I'm Heng Han. And today I will be giving a presentation of the capstone project that I've been working on for my final semester, and it is the automated measurement of Cobb angle from spine image. My mentor is Professor Matthew Chua, and I'm Heng Han here. Without further ado, I will share the agenda of the presentation. I'll first start off by giving the introduction, share its background, as well as the past research works. I will then share the proposed solution as well as its novelty. And finally, I will highlight the experimental results before I end the presentation with the conclusion. The introduction will give a brief introduction on spine deformity, share its causes as well as methods used to measure and manage spine curve. So what is scoliosis? Scoliosis is the curvature of the spine and is measured using the Cobb method. There are three different types of spine curve, namely the idiopathic, where there is no known cause for it. The second type is congenital, which is due to genetic disorder. And the third type is neuromuscular, a disease related to nerves and muscles. Of these three types, idiopathic is most commonly seen and the cause for it remains unknown. And if scoliosis is not treated, it will lead to curve progression and other complications such as pain, shortness of breath, and even low self-esteem. Today, the treatment types includes wearing a brace or undergoing operation to correct the spine posture. In this section, I will highlight the problems faced when measuring the degree of spine curve. So how is spine curve measured and what are the challenges faced? First, the assessment is done manually using X-ray and measurement tools. Second, every patient has different physical body size and mass, which will affect the assessment. Third, X-ray images may contain contrast issues due to low tissue. And when the measurements are done across different experts, there is a large inter or intra-observer errors. And this means that there is a need for an alternative solution that can help to automate as well as removing the variance and bias in the process of Cobb angle measurement. Now I will share the previous research works. Past research works typically entail a four-step approach that first performs image pre-processing, then the spine is identified through windowing. Next, using convolutional neural network to segment the vertebrae, which is the tiny bones that form the spine, and finally to estimate the curve angle using computer-aided means such as curve fitting method. In this section, I will be presenting the system pipeline, image segmentation architecture, and algorithm used to compute the Cobb angle. The proposed system pipeline architecture includes developing a segmentation network coined as UMesh network, a deep learning model that leverages computer vision capabilities, and a Cobb angle algorithm that uses distance between extreme points of a contour and trigonometry method to calculate the output angle. Two versions were created. The first was based on a single-stage segmentation network. However, after training my model, I believe that the experimental results could have been better, and hence, I tweaked the architecture by introducing an additional stage of segmentation to segment the spine region, which could be seen in the orange box. In this proposed image segmentation architecture, it combines upsampled features and long short skip connections. It comprises three key features. First, long skip connections in gray arrows provide high resolution features that help to recover spatial information. Second, the short skip connections in purple color enables deeper FCN. And third, the upsampled features in green color help to focus on feature boundaries. The aim of using these features is targeted at rendering more accurate segmentation results. The second part of this solution is the derivation of an algorithm for Cobb angle measurement. The first part is involved in finding the contours for all vertebrae, as well as the extreme points in each contour. The second part touches on calculating the gradient angle of a vertebra. And last, the Cobb angle is computed by summing the most tilted vertebra in both positive and negative gradient. In this section, I will highlight the novelties that were introduced in the proposed system architecture. There are two main novelties introduced in this system architecture. First, it is focused on the quality of segmentation results by combining upsampled features and long-short skip connections. Second, it refers to multiple spine regions for scoliosis assessment. Now we will share and highlight the experimental results of the proposed solution. Two experiments were conducted. Experiment 1 represents the proposed solution, which uses a two-stage segmentation network, while experiment 2 is based on a single-stage segmentation. There are two objectives. First, to compare between UMesh network and UNet. Second, to determine whether multiple stages of segmentation and its annotated labels have an impact on the overall system performance. In Table 1, we reference to the highest die score across the 5 folds. UMesh is almost on par with UNet in Experiment 1. However, UMesh network has outperformed UNet by 8% in Experiment 2. When comparing the best die score for vertebrae segmentation between Experiment 1 and 2 of Table 1, it could be noticed that a two-stage segmentation network has outperformed a single stage of segmentation by at least 8%. This is evident by the fact that the first stage of segmentation has helped in isolating the spine from the entire X-ray image, which allows the second stage of segmentation to focus on identifying the vertebrae within the spine region. However, interestingly, in Table 2, the total error in Experiment 1 is at maximum 35% higher than in Experiment 2. This is likely due to the weakly annotated labels for both spine and vertebrae, which suggests the partial reason of the underperformance in predicting the vertebrae output. The experimental results show that two-stage of segmentation is better than a single stage, and UMesh network has outperformed UNet network. The one-way ANOVA analysis is used to compare the statistical results between the proposed algorithm 1 and the manual measurements obtained from human calculation. 30 test samples were recorded for use. The null hypothesis states that the mean of all assessors is equal, while the alternate hypothesis states that at least one of the means is different. P-value of 0.05 was used to decide which hypothesis is to be accepted. The p-values indicated in the table for all three spine regions were greater than 0.05. It indicated the acceptance of the null hypothesis and signified that there was no significant difference in the Cobb angle measurement between the selected assessor groups. And with this, I will come to the end of the conclusion to conclude and summarize the entire project. In conclusion, deep learning performance surpasses traditional solutions. And when deep learning is coupled with other techniques such as computer vision, it is a powerful combination that could create impressive and automated solutions. This project benefits the community in the sense that it allows future researchers to bring this to the next level, and it also enables the clinician expert to focus on other higher value works instead of measuring the Cobb angle manually. As mentioned earlier, the first novelty introduced in this project uses upsample features and long short skip connections that aims to obtain accurate segmentation results. The second novelty comprises a wide coverage scoliosis assessment, which is achieved by focusing on different spine regions. With this, I will then move on to a demonstration of the application that I've developed. This is a pre-recorded video. The main script is to start the application using the autoassess.py that was created. The remaining Python script are the respective subprograms. And there are two model weights, one for spine prediction and another for vertebrae prediction. The top left shows the GUI of the script that I have created. I'll start off by selecting an image. This is the original file. You could see that it's pretty bad, and now this is the classy file that has been processed to make it brighter. And this is the resize file before it's fed into the training model. Now I'll predict the spine mass using the pre-trained weights and the resize image file. And this is the results obtained. The spine mass is created. Next, I will predict the vertebrae mass using the pre-trained weights and the spine region image file. This is the predicted vertebrae mass, as we could see shortly. And the vertebrae was not completely identified, and my assessment is that the annotated labels were not accurately created, and there still exists low tissue contrast in the image. And one way to overcome the prediction is by using a larger image resolution. Now I'll use the developed algorithm to compute the Cobb angle, and this will be performed on a test mask that was created. From this image, you could see that the algorithm has successfully computed the angle for the 3 spine regions. So on this result itself, we could see that the algorithm is able to determine the curve of the spine in 3 different sections, namely the cervical, the thoracic, and the lumbar. And with this, I've come to the end of my demonstration. Thank you for your time.